The F1F0 ATP synthase plays a critical role in the synthesis of ATP, which, as we all know, is crucial for most of life's processes. In this lesson, we're going to focus on the F1F0 ATP synthase, which is one of my favorite enzymes, and I think a favorite of many people that love enzymes and that love protein structure. We will explore what is called the binding change model that Paul Boyer first proposed for how ATP synthesis is achieved, and then apply a variety of experimental approaches to confirm specific aspects of the synthase's mechanism of action. The structure and functional mechanisms of the synthase were discovered by the combined work of Paul Boyer, a biochemist at UCLA, and John Walker, a structural biologist at the MRC in Cambridge, and represents one of the most important collaborations between biochemistry and structural biology in recent memory. For their efforts in uncovering the structure and function of this enzyme, Boyer and Walker shared the 1997 Nobel Prize in Chemistry with Jen School. At a mechanistic level, we will explore how the F1F0 ATP synthase harnesses the energy of the proton gradient in mitochondria to synthesize ATP. This will help us really explain how the protons pumped by the electron transport chain actually provide the energy for ATP synthesis. To understand the workings of this truly amazing molecular machine, we will define the major protein components of the synthase complex and then what they contribute to its mechanism of action. The F1F0 ATP synthase is an example of an F-class pump. There are other classes of transmembrane pumps that hydrolyze ATP to actively transport cargo across membranes. But in the case of the ATP synthase, it utilizes the movement of protons across the inner mitochondrial membrane to drive the synthesis of ATP. The ATP synthase has multiple protein subunits that are clustered into two major components: the so-called F0 complex and the F1 complex. The F0 complex is a proton channel and is where protons flow across the inner membrane of the mitochondrion. The F0 contains three different subunits, A, B, and C. The C subunits assemble into a ring-like structure within the inner mitochondrial membrane, and the proton channel lies at the interface between this so-called C ring and the A subunit. In contrast, the F1 complex is the site of ATP synthesis. It is composed of 5 types of subunits: alpha, beta, gamma, delta, and epsilon. The components of the synthase most directly involved in the synthesis reaction are the 3 pairs of alpha and beta heterodimers. Together, these 3 pairs form a hexamer and comprise the mushroom head of the synthase, which faces into the mitochondrial matrix. This is the site of ATP formation, where actual enzyme catalysis is performed by the beta subunit. The gamma subunit links the hexamer to the inner portion of the C ring of the F0 complex. It is the rotating axis, therefore, of the complex of the synthase. The delta subunit, on the other hand, anchors the hexamer to the B subunit that is embedded in the membrane. The delta subunit effectively stabilizes the hexamer and holds it in place, and prevents the hexamer itself from rotating. Thus, when the C ring rotates, it in turn rotates the gamma and epsilon subunits, but does not rotate the hexamer itself.